And so this last video is for part C of June 2017. And so we have 66 through 85, that's part C. 66 through 70, this whole set is based on the skier being towed up a hill by a tow rope. So let's take a look. All right, so there's a bunch going on here. We have a 72 kilogram skier. So we know the mass of the skier, 72 kilograms. And going from the bottom of a hill to the top of a hill, the change in height is 40 meters. And then the distance that the skier goes along the hill is 230 meters. And then it says that the pulling force is 158 newtons. 158 newtons. And it's at constant speed. Constant speed. So no acceleration. And that's the stuff that we know. It says, what is the work done by the rope on the skier? And so the work done by the rope is the force of the rope times the displacement along the hill that the rope was acting. So again, the force and the displacement need to be in the same direction. So the force was the pulling force along the hill surface, and the distance of the hill is 230 meters. Multiplying together, we get 36,340 joules. Controlling for sig figs, that'd be 36,300 joules. But I'm going to leave it with all of the digits because I feel like I'm going to be using that work number in the next question, which is how much gravitational potential energy? Oh, no, that's actually fine, the gravitational potential energy, but they're going to be hinting at the difference in following questions. So gravitational potential energy and mg delta H for gravitational potential energy, I only get 28,300 joules. So there was 36,300 joules of work done, but the actual gain of energy, the gravitational potential energy gain, is only 28,300 joules. And you could say, well, there's kinetic energy gain, but there isn't kinetic energy gain because it's a constant speed. So there was no gain in kinetic energy. So yeah, the work that's done by the tow rope pulling the skier up the hill should equal just the gravitational potential energy. But obviously it doesn't, because if there's friction, there's going to be some loss to internal energy or heat. And so what happens to the internal energy of the skier hill system as the skier is pulled up the hill? So yeah, since that gravitational potential energy output is less than the work that was input, there's heat that is lost to the skier hill system. I guess you could say that the internal energy, since heat goes to the skier hill system, so therefore the internal energy of the skier hill system increases because the heat goes into the skier hill system. All right. What happens to the total mechanical energy of the skier hill system as the skier is pulled up the hill? Now this one's a little bit tricky because usually total mechanical energy is conserved, but total mechanical energy is conserved when there's no friction. But in this case, there is friction, and friction is doing work causing heat to be transferred to the skier hill system. So let's recall that total mechanical energy is equal to gravitational potential plus kinetic. And so the work that's done, the work that's being input into the system, is greater than the total mechanical energy because it's greater than gravitational potential and there is no gain in kinetic, it's constant speed. So the total mechanical energy of the skier hill system as the skier is pulled up the hill, so the total mechanical energy of the skier hill system does increase. However, some of that energy, some of the total mechanical energy is lost as heat or internal energy, otherwise known as heat. The short answer is that the total mechanical energy increases, period. It doesn't say explain what happens, it just says describe what happens. It increases. And the reason why it increases is because gravitational potential energy increases. You don't have to explain it, but I'm explaining it to you because you should know why it's true. That's the point of a solution video. I don't just give the answers, I also try and explain why it's so. All right, anyway, so that was number 70. We still have to get up to number 85. So 71 through 76 is based on this lovely parallel circuit. Okay, so we know the individual resistors, and 71, 72, what's the equivalent resistance of those two? I can tell you it's not 45 ohms. We don't simply add them together in a parallel circuit. So I have 1 over 15 plus 1 over 30 is 0.1, and so R equivalent is not 0.1. 1 over R equivalent is 0.1, so then R equivalent is 1 over 0.1, 0.1, which is equal to 10 ohms. And yes, the R equivalent for the entire circuit is less than the individuals. That's the way parallel circuits work. As you add resistors in parallel, equivalent resistance goes down. So that was a 2-point question, so you would need to show work, including the equation for that problem. Then 73, the current measured by the ammeter. The ammeter is in series with the power supply, which means that that ammeter is measuring total current. I know the total voltage, and now I know the equivalent resistance. I can do R equals V over I and solve for I get 6 amps for 73. Then 74, 75, the rate at which the battery supplies energy to the circuit. So the rate at which the battery supplies energy. So we're not looking for energy, we're looking for the rate of energy, which is the power. So what is the power? Well, I know voltage, current, and resistance, so I can really use any of those two to get power. Why not go with the simplest way to do it? Power is VI, the voltage of the battery times the current coming out of it. Or it's not coming out of it, the current pushed by it. And so that would be 60 volts for the battery, and then 6 amps for the current, giving me 360 watts for the power. And that is a 2-point question, so that would also need an equation and substitution with units. And then finally 76 says, if you added another resistor in parallel, what effect would that have on R1? So in parallel, the circuit elements are independent, so if I added another resistor, they would have no effect on R1. It would increase the total current because you're decreasing the equivalent to the total resistance, but that's because that resistor would draw its own current as if it were by itself, because it would be acting independently. And so there's no effect on R1. All right. Okay, so that was 76. Now we have 77 through 80, and then I bet the next question, 81 through 85, is the last question set. So let's take a look at 77 through 80. We have two 2-point questions, two show the work questions. So let's see what we have. A gas-powered model airplane is a mass of 2.5 kilograms. Student exerts a force on a cord to keep the airplane flying around her at a constant speed of 18 meters per second in a horizontal circular path with a radius of 25 meters. What is the kinetic energy of the moving airplane? Well, I was going to start, let me write down the given information. I think 77, 78 is kind of simple, but I'm going to write down the given information anyway. So I know the mass is 2.5 kilograms. I know that the speed is 18 meters per second squared, and I know the radius is 25 meters. And I know it's moving in a circle that looks like Serta, circle at a constant speed. And 77, 78. Find the kinetic energy of the moving airplane. That's pretty basic. 1/2 mv squared on the back page of the reference table. Just don't forget to square the speed. So 1/2 times 2.5 kilograms times that 18 meters per second. Don't forget to square the speed. And we get 405 right on the money, and that would be joules because it's energy. Then 79 and 80. All right, 79, 80. Centripetal force to keep it moving in a circular path. Well, centripetal force is mass times centripetal acceleration, and centripetal acceleration is speed squared over the radius, and they go together so often as Fc equals mv squared over r. Technically, that equation as written is not in the data booklet, but they use it so often, like now. And so, anyway, we're going to put in the mass, 2.5 kilograms. We're going to put in that speed, and we're going to square it, 18 meters per second squared. And the radius of the circle is 25 meters. And let's do that math. So the centripetal force winds up being 32.4, and it's a force, so that would be in newtons. All right, and that also is a 2-point problem, so you would need to show an equation, some version, F equals ma, AC is v squared over r, FC is mv squared over r, some version of that with unit substitution and units with your answer. All right, why stop now? Let's finish this sucker. So the last problem set involves some kind of refraction situation. We have the normal, and we have medium x, and we have air. So I'm assuming that this is not just where the ray is going, but this is also the boundary, interestingly. And it says that, let's see, it doesn't actually say, basically the prism that they're working with is actually a rounded prism. They don't all have to be blocks of glass. It looks like a protractor. It is actually a piece of medium X, whatever that is actually rounded. And the reason why that is because the ray is coming in, and the ray is actually coming in perpendicular to the boundary at this point right here. And so there's going to be no refraction as it enters the medium. And very interestingly, it says big to little bends away. So we are going from medium X to air. Anything is larger than air, so we are bending away from the normal. But it seems that we're bending so far away from the normal that the angle of refraction is 90 degrees. This is the refracted ray, and this right here would be theta 2. But we can clearly see that that is 90 degrees. Very interesting. Let's check it out. Ray of light, frequency of 5.09 times 10 to the 14 hertz. That's the reference frequency that they use for the index of refraction chart. We don't know what medium X is, but we know the angle of refraction is 90 degrees. It even says so in the description. Weird, but okay. And so 8182, calculate the wavelength of the light ray in air. Well, I know the frequency, and I know that it's light in air, so this is going to be a V equals F lambda situation, where V is c, the speed of light in vacuum. You can look that up on page 1 of the ref tabs. So I divide both sides by the frequency to get wavelength, and wavelength is 589 nanometers, 5.89 times 10 to the negative 7 meters. Here's our wavelength. 2-point problem, so make sure the equation is there with units and units with your answer. 83. Measure the angle of incidence for the light ray incident at point P and record the value in your answer booklet. So angle of incidence, that's going to be theta 1 right there. Now the cool thing about pinch to zoom, that no matter what your scale is, it changes your scale in terms of lengths, but angles remain the same. So let's see what that, let's pull out I'm going to sketch in my handy dandy Phaco protractor, super Phaco. That's looking like 45 degrees, but I'm going to pull out my actual protractor and I'm going to actually check it. Alright, I checked that with my protractor and I get an angle of incidence. No, I don't want blue. I want black. I know, the color doesn't actually matter. It matters to me. Theta, 50, not 5 degrees. It's pushing on 10 o'clock at night. I need to go to bed. 50 degrees, plus or minus 2 degrees. So that means anywhere from 48 degrees to 52 degrees. So yeah, it was close to 45, but if you said 45, you would be out of range. You'd be well out of range because you get anywhere from 48 to 52. So 45 is 3 degrees away from the lower limit. All right, anyway, so calculate the index of refraction for medium X. Now that I know the two angles, theta 1 and theta 2, I can use Snell's law to calculate the angle of the index of refraction for medium X. And all right, so we have N2 is air and the theta 2 is 90 degrees, so sine of 90 is 1. So really, I just wind up with N1 sine of 50 is equal to 1. So then N1 is 1 over the sine of 50 degrees, and so that gets us 1.3. Be in degree mode. And there you have it. Incidentally, what we're seeing here, it's kind of like what even is that? You know, when the angle of refraction is 90 degrees, the ray is along the boundary. Like, what's up with that? And if you remember from when we did, now if we use this video in subsequent years, maybe we won't do this lab. I don't know, whatever. Currently, it's 2023, and we did a lab using Colorado FET simulation of reflection and refraction, and at the end of the lab, there was a point where the ray disappeared. And the reason why that happens is because there's something called the critical angle, where there will be no refraction, where the ray will not enter the new medium and it will completely reflect off of the boundary. And that complete reflection happens at angles, at incident angles. Basically, let's go back to the incident angle, that 50 degrees, that's called the critical angle. If you go just a smidge above 50 degrees, you will have complete reflection and you will have no entering into the new medium. You actually see this if you're underwater in a pool and you look straight up, you can see the ceiling through the water. It's going to be ripply because you're in the water. But then if you lower your eye angle along the water surface, you'll notice that eventually you can't see through the water anymore, and you'll just see a reflection of the bottom of the pool. And that is what is happening. That's called total internal reflection. That principle is what keeps a laser beam inside of a fiber optic cable. So when they send optical signals through fiber optic cable for, say, like, the internet, like the whole thing, that's how it works, and that's why the laser doesn't escape outside of the fiber optic cable until it reaches the end. Pretty cool. All right. Anyway, so that was the last question. Congratulations, that's the end of the 2017 Regents, and that's the end of this video for Part C. Right on the money for 19 minutes.